In this lecture, we will implement combiners based on conc trees that we introduced in the previous lectures. We will call this new combiner implementation a conc buffer. Internally, a conc buffer contains a conc tree and an array of a fixed size k, where k is a predefined constant. It also contains a field chunk size, which holds the index of the first empty array entry. Let's visualize this array named chunk. As long as the array is not full, conc buffer adds the elements to the first non-empty array entry. Once the array becomes full, we simply push the entire array as a leaf in the conc tree and allocate a new array. If the chunk size is full, we call the expand method, used to push the array into the conc tree. In any case, we write the element to the last array entry and increase chunk size. The magic ingredient here is in the expand method, which we will show shortly. To push the array into the conc tree, we will introduce a new node type called chunk. The chunk class holds the array and the number of elements in it. The level of the chunk node is 0, just as it was for single nodes. With this new node type, the expand method becomes simple. It creates a new chunk object, calls the appendLeaf method from the previous lecture to push the chunk into the tree, and then allocates a new array of size k and resets the chunk size counter. The combine method is what you'd expect. It calls the result method on the two conc buffers to obtain their conc trees, and then concatenates them into a new conc tree. Finally, it returns a new conc buffer which contains this tree. Method result must create a conc tree from the contents of the buffer. To do this, it appends the element array to the conc tree as a chunk node, similar to what the expand method does. To test the performance of the conc buffer, we will use it in exactly the same benchmark as we used array combiners in. We will copy the contents of a sequence in parallel using the aggregate method and then output the result. We first create a custom scalameter configuration. In the main method, we declare the size of the conc buffers to be 1 million elements, and then we call the nested run method 4 times with different parallelism levels 1, 2, 4, and 8. The nested run method first creates a new scheduler with the desired parallelism level, and then initializes an array of strings used to call the aggregate on. It then creates a parallel collection, sets the custom scheduler, and measures the time required for this parallel operation. Finally, it prints the parallelism level and the running time. So let's run this program. For one processor, the running time is around 15 milliseconds. For two processors, this operation scales almost linearly. The running time is 8.2 milliseconds. For 4 processors, we start noticing some memory contention. The running time is now 5.8 milliseconds. Since this processor has 4 cores with hyperthreading, it is not reasonable to expect any significant gains with higher parallelism. Still, the running time is slightly better than before at 5.4 milliseconds.